systems. So yeah, thanks.
Yeah, thanks for a very nice introduction. I think everyone can hear the mic. Okay. Yes. So unfortunately, I know there have been lots of very practical and sort of useful things already happening in the morning. This is going to be a theory talk. I'm not going to hide, but I'll try to do my job and sort of make, hopefully contribute to this quantum industry day. And so the very topic is going to be quantum simulation. As you see, this has been really been one of the earliest and still today kind of a very lasting topic. As Dan say, this interaction between physics and computation sort of, it seems like will go a very long way. And then I'm supported by CIQC, which has generously allowed me to sort of also visit other schools such as MIT. And then this sort of camp of sort of thermal simulation and this Gibbs sampling really have benefited a lot from the vibrant environment created by Simon. So that's really very grateful. Okay, so let's get started. Just to guide the discussion, suppose we have some concrete model we would like to simulate. Say it's a Fermi harbor on a 10 by 10 lattice. We don't have to be attached to this model, but let's say this is a concrete example, and we'd like to study some property out of it, right? And then very concretely, we can say we probably would be interested in understanding some low temperature properties. If you want to study some superconductivity, we probably want to know some phase diagram or some kind of conductivity type of property. And if that's our goal, then what is the algorithm? And today I'm going to sell you an algorithm, which is probably sort of characterized by these two. So it's going to be like a bath simulator or like a digital refrigerator that emulates nature's sort of cooling dynamics. And then in more computer science terms, this would be called like quantum Gibbs sampling as sort of like a salute to classical Gibbs sampling. Okay, so that is going to be the plan for today. So just to take a bit of a step back, if when I talk about quantum simulation, quite often this is what many people would think about. This idea really have go back very long way to Feynman when we talk about sort of how to simulate quantum using quantum computers, and then this idea of just directly simulate the laws of physics. If you give me a quantum state, this initial state, and then I evolve it, this e to the IHT. And in principle, this kind of describes everything, in principle, right? And so far, this has really been kind of now very, very well grounded in the community of quantum algorithms. There's just been so many algorithms we can find right now is highly optimized that basically carry out this task sort of without a doubt. Okay. And then also very nice, what's also very nice about sort of this dynamical simulation is that people probably believe it's classically hard, meaning there are some instances where this is just very classically very hard to do. And now we don't really have like a universal classical algorithm to do this efficiently because these matrices are all very, very large. So that seems to be a pretty nice kind of collection of features of dynamic simulation. However, there's like a somewhat serious caveat is that if you really sit down and say, oh, I'm going to extract my superconductor data out of this equation, how do you actually do that, right? So first you have to pick some initial state, and how do you pick this, right? Someone has to pick a state and evolve, and then supposedly it must be able to extract some data. But it just doesn't somehow not really obvious, at least to me. If you just look at this, how do you get that data out? Okay, and I think many people will also agree. So this is not very obvious. So then, there's also like a different camp of ideas that recently people start thinking, well, maybe we should directly have something more concrete and kind of these notion called thermal equilibrium that we should just aim for those. Okay. And then this is a very, very well-defined, mathematically clean problem. It's given a Hamiltonian, given a temperature, you want to simulate sort of the thermal state. Right? This is really, you can look at this up in the physics textbook. This is a very very well-defined long history object. And then physicists throughout the way has really been able to just get a lot of data out of this object. Right? You can calculate, and if you really have a quantum state in your lab, you could just directly measure properties for this state. So this, in principle, seems to provide like alternative answer to quantum simulation. Is that if you have a Gibbs state, it looks like I can also do many things. Okay. And then part of the reason why this kind of effective thermal equilibrium picture has been nice is that it's very clean. That it's easy to describe what we are aiming for. So there's a very clear goal, and also it has just been working just very, very well. It captures a lot of things we see in nature. There's very clean theory behind it. It matches the experiment seems pretty well. At the same time, even though it kind of captures many things, the skip state are also kind of happen to be very kind. Like they're very friendly to the theorists that they have lots of structures that we can use to attack them. So somehow the thermal equilibrium state lies in some sweet spot between being very expressive and very structured that allows a lot of the progress. And then for some of you who have been keeping track of the recent kind of quantum / many body physics program, there's idea of such a that has made this very useful is an area law that for example it really helps us sort of understand these low temperature physically existing many body states. Okay, so if this is then the goal we are interested in, then the main algorithm we're going to propose today is that, well, if you want to thermalize, why don't you just do what nature is doing? Presumably this is dilution fridge. So then you can ask, okay, so let's try to set up a concrete algorithm that's sort of motivated by nature. Okay, so in physics terms, this is called a Lambdatian or master equation. It is some kind of continuous time dynamics describing a quantum system interacting with a bath, right? And then if you're going to write down a mathematical clean description of what this L is, this Lambdatian is, you kind of hope that it morally captures what this refrigerator is doing, but somehow throw away sort of enough detail so that it can be simple enough that you can simulate it efficiently. Right, so you're kind of hoping to get like a simple enough effective description that capture the core kind of mechanism behind sort of the refrigerator. Okay. And then for the computer science-minded audience, this is you can completely rethink about this as nature's quantum Markov chain, or quantum Gibbs samplers. And then if you're thinking about this more like designing an algorithm, you kind of hope something that is simple enough that you can analyze and to implement it, and you also hope that this is somewhat consistent with equilibrium physics. And for example, you sort of want this Markov chain, if you keep evolving it, you should converge to the Gibbs state, if that is sort of the equilibrium state. Okay. So these are sort of the things that we would like to have if you're going to have a bath simulating algorithm. And then there's a recent line of work that achieves some of this, and then there's been lots of recent algorithmic follow-ups that make this more and more complete. So the claim is that there is such a construction, and I will call this quantum Gibbs sampler, that essentially mimics the properties of Glauber dynamics. So Glauber dynamics is one of our sort of canonically used classical Markov chain algorithms. And then and then if you have an Ising model and you want to do some thermalizing dynamics, Glauber just basically randomly pick a spot and then look at its neighbor and then do some update randomly. Right. And then and the claim is that these quantum Gibbs samplers are very similar in some way. I claim that it's also quasi-local and have some detail balance property. But then because of some quantum mechanical features, the map you're doing has to be somehow delocalized. But it's still quasi-local, so then I draw this blob to represent this non-locality. But then the claim is that somehow there's a way to kind of incorporate all these kind of measurements, rejection steps, all these things all together in an abstract kind of Lambdatian that achieve all of this. Okay, so the details are all in the papers. They're pretty complicated, but at least there is such an algorithm. So in principle, this is one kind of a concrete algorithm that one can use to simulate many-body thermal physics. And of course, there's must be still a long way to actually implement these things. And I think there's been lots of very, very recent progress that I'm not even able to keep track of that try to significantly simplify these recent construction. And I believe there are also industry attempts to simulate some version of these system bath interaction. Okay. And then I would say, at this time, if you're more theoretical minded, it's actually a pretty exciting time to do this kind of Markov chain theory. If you just think about how fruitful the study of Markov chain has been in the past 40 years. Okay? And then practically, if we're theorists, we should be prepared when experimentalists are actually able to run this. Right? We should be able to predict and then try to match experiment and be welcome to surprises. And then just to kind of flash some of the recent developments, having this new dynamical approach to thermal equilibrium has actually allows us to revisit some of the very old properties of thermal equilibrium states, actually tell you something new about this very old subject. And then it gives you some new tool you can play around. It's a sort of a new algorithmic tool. That's recently has been started gaining traction. And then for the remaining of the talk, I will talk about sort of even more creative kind of part of this agenda is that it actually allows you to define completely new problems in a very precise way about how we think about out of equilibrium physics. So today, for the rest of the talk, I'll focus on this very recent work, was posted just last week with Umesh and then Tiago, who's a very good grad student here. Feel welcome to talk to them. Okay, so so far I have been lying to you a little bit. So there's actually a fundamental caveat in thermal simulation that as a theorist, if you ever thought about these problems, this once in a while would come up in your head. So the caveat is that this problem I just defined, this Gibbs-Simons problem, is actually computationally intractable. Okay, and this is all backed theoretically. There are instances where this just seems really, really hard to solve. And then, okay, so what to do with that, right? And practically what that means is that if someone walked to you and say, I have a universal kind of, fully universal Gibbs sampling algorithm, you might be skeptical because of this hardness. And what it means is that it just seems pretty hard to have like a completely kind of black box guarantee of how your algorithm is actually going to do, right? And then it might mean that, practically you might just have to change, or like you have to re-estimate all the costs of their algorithm if someone just gives you a new instance of algorithm or a new instance of Hamiltonian. And then concretely, this goes into the form of mixing time, trial state, gap adiabatic paths. And so far, there's really not like a simple solution to it, right? And then you can ask, is this like just like artificial problem in the proof? Maybe everything in real life actually works. However, from physical standing point, actually, a lot of physically interesting system does exhibit, slowdown mixing, does exhibit phase transition, and does exhibit strong correlation. So maybe, part of this hardness is actually also physical. But then the question is, then how do we actually go about this problem? How do we redefine sort of a thermal simulation problem? Okay. So really the main kind of one of the main motivation for studying metastability is to kind of, if you look around a room, you'll start looking at a lot of things that looks stationary. It looks very robust. Like if I knock this table, it seems it doesn't break immediately, right? But if you now think that, okay, if Gibbs state is not really going to be the fundamental object, if it's sort of not in true equilibrium, then this thing you look at is probably not really the Gibbs state. So it has to be something else. But then it looks thermal in many ways. Okay? And I guess this figure is supposedly an insect being trapped in an ember and then has been there for a million years or something. Okay? So, but eventually this thing got a break, but somehow it looks pretty stable. Okay? So if that is the thing we really care about, and that's the thing that nature is really doing, from our childhood, probably at some point have this kind of local minima picture that we would think that maybe the things that you actually see in real life is probably something trapped in some kind of local minima, in some very heuristic and oversimplified landscape picture. Because indeed, eventually, all these chemicals eventually they react to something else. They eventually dissolve. If you have a hard drive, eventually something happens and you lose the memory in a hard drive. Right? So this idea of metastability or something being some kind of local minima, but not exactly Gibbs state, seems to be very present. But the question is, how do we actually try to capture this? Right? So if this is going to be a theoretical kind of investigation, there's actually been lots of attempts to do this. We're really not the first one to try to do this. But sort of really the recent push sort of from the computational lens and so making things more precise is a lot more recent. And then perhaps one kind of more recent related work is this local minimum quantum system. Maybe some of you have heard, right? But somehow the point is that in constant temperature, somehow in this work we're able to reveal somehow quite different kind of structural consequences in these sort of thermal phenomena. Okay. Okay, so this is a theory talk, so I have to put down some definition of how we go about formalizing these metastable states. So here's a definition that we end up find very useful and kind of clean and succinct. So we say a state is metastable if it's sort of changing slowly, right? So this L is really just the time derivative, and we're just saying the time derivative of state is sort of very small. Okay, so we say it's approximately stationary, then it's metastable. And then physically means that if you try to observe anything out of a statistical property out of this state, it's just not really changing very much. And such a property could be such as an energy, but it also could be other kind of local observables. And this is really an instantaneous notion that we try to define. It doesn't care about how the state becomes metastable. It's just that for this instant, it looks like it's not changing. Okay, so with this definition, the claim of this paper is that there seems to be a very clean and nice theory of metastability under this definition. Okay? And we claim that there's simultaneous kind of properties of metastable state that make them kind of nice and friendly, and hopefully that also tells us something about what we really want to simulate in quantum simulation. So here are the list of properties that first is very structured and kind of resembles a lot of the things we really like about Gibbs state and ground state, is that it has an area law. So these states are somehow very structured and constrained. Okay, they're not just any state, they're pretty special. Also, they satisfy some kind of noise resilient property that without explaining right now, it somehow resembles the fact that when you do this, the table doesn't break. That is a first order approximation of what that means. And then at the same time, in this simulation context, this metastable state turns out to also be efficiently preparable. Right? So somehow it has a collection of lots of very nice property that perhaps could make it a candidate for what we're really interested in simulating. Okay, and a lot of tools we use actually sort of are inspired by related kind of classical Markov chain techniques that helps drive our framework. Okay, so let me just go through these three properties. So just to recap, the area law has been very well like one of the key fundamental structures to understand low temperature states that really enables a lot of classical algorithm and also theoretical method to understand these low temperature states. And then what we're able to show is that if you have a metastable state that you don't know how it came from, but it just looks stationary with some error epsilon, then we claim that it also approximately satisfies an area law. Okay, so I don't have time to directly define this, but this is a mutual information. It's some quantity indicating how correlated are between a region A and its complement. Okay, and the surprising thing is that this correlation really only scales with the area, but not the volume. So this is sort of the key of this idea of area law. But then they also have some correction that's coming from metastability. Okay, right now I don't have time to fully describe all these parameters, but there is a bound, and if you're interested, we can talk more. But roughly there is an area law. Okay. And then second, on top of this correlation structure, metastable states are also noise robust. Okay, somehow. And it seems, the more I think about it, it feels kind of weird because these states are supposed to be very quantum mechanical objects, but somehow there's a very natural sense of noise robustness. So here's a claim. So if you take some object that looks very metastable, and then you apply some noise to some part of the system. Okay? The claim is that there is like a localized recovery map that if you just act kind of around that region, you're able to recover the full state. Right, so this is so-called Markov property, but you can also interpret it as some kind of noise robustness of these states. Okay. And in particular, this works at any temperature, any dimension, and this somehow doesn't care about phase transition. This Gibbs state could be in a critical state, and this still holds. Or in particular, if you think about a random hard random state, it wouldn't have this property. This is really some kind of some people would say this is a version of conditional dependence in a quantum world. Okay, so I'm not going to lie. This recovery map is secretly just again some kind of Gibbs sampling map. So really, the intuition is that if someone poke a hole on your sample, the way to recover it is to turn a heat sort of around that sample. And that's algorithmically what it's really just doing. It corresponds to really turn on a Gibbs sampler or this Lindbladian around these region you would like to recover, and the claim is that it does work, and there's a proof that it works. Okay. And then for those of you who are interested in quantum algorithms, this is a way to kind of think about conditioning on a quantum system. And there's very subtle ways that this compares with the classical case, because quantumly conditioning is quite a weird and spooky idea. Okay. And then practically, it looks like this might give a way to reuse complex quantum state that would actually revisit very soon. Okay. Okay. So since we're in this industry day, we'll have to talk about some applications. So in this third property of metastable state, the claim is that they're also very kind of algorithmically very friendly. Okay. So and here's a claim. If you have initial state, you want to make it metastable, you can always do it. Right. So the claim is that if you initialize with any state you like, evolve for random time, it becomes a metastable state. And then this actually gives you like a very clean and end-to-end experimental protocol to study these metastable state. You can just repeat this, and then you can get all the data you would like about this particular metastable state. And then you can change for different initial states, and that could, in principle, give you very different looking metastable state. And pictorially, if you go back to this heuristic kind of bottom well picture, in the initial state may look kind of really awkward and not metastable. But then when you kind of do some kind of random time dynamics, you actually really stabilize, in some kind of mixture of many different wells. Okay, and then it might be hard to control which ones you're really landing at. It most likely would depend on where you start. But then you're able to kind of, when you do the measurements, you're able to see the statistics corresponding to a mixture of these different wells. But then you may say, well, if there's really this kind of bottom wells picture, we might want to isolate individual of them if they somehow kind of generate kind of all these possible statistics, right? So you can ask, okay, how do we really probe this individual well? So then there's become a pretty interesting, but I guess more heuristic question. So if we try to do something a bit more clever and more hopeful, so what if we don't reinitialize? So we just keep measuring and resample. So almost like running a Monte Carlo algorithm, right? So suppose you want to do a measurements with your metastable state, and mathematically you can write this in terms of some quantum channel. And then the first thing you might notice is that this mixture of well may soon collapse into individual ones. And then if this measurement kind of distinguish these different ones, you might start kind of collapsing into individual ones. Okay? And if it happened to be the case that the picture looks like this is really just in one of these bottom well, then this is something that could happen, right? So if there's really just one well, and this metastable state is lying very nicely here, and then you do a measurement, and if this measurement sort of is not too crazy that it doesn't kick it really out of the well, I pictorially draw two different types of disturbance within the well. And then you will collect some observation, with the corresponding probability, right? But then it could be that if you just run this thermalization dynamics, it quickly restores to the same metastable state. And if this is the case, then you can just reuse this, so you don't actually have to restart the whole process. And that seems kind of very efficient if it's really possible, right? But I'm throwing out this picture. This is sort of something that I believe could happen in some systems. And if that is the case, it just seems very, very convenient and could really speed up all these tomography or measurement schemes for these many-body quantum states. Okay? And then, just like in Markov chains, if you want to explore other kind of these local minimas, you could do some more violent move, and then it could completely kick you out of the local minima. And then you might have to wait a bit to kind of wait to restabilize into one of them. Okay. Yeah, so that's morally the story I would like to tell. And then sort of I would just like to end here with sort of a hope for to conclude and hope for quantum thermal simulation. So in the beginning, we have started with this dynamical picture that is very well understood. Maybe it's very unstructured, but it's always kind of algorithmically feasible. And then I also mentioned this equilibrium approach that's more direct, more structured, easier to study, easier to extract data, but turns out to be computationally infeasible. Okay. So the picture that I was trying to convey is that it seems that for metastable states, now that we have developed some of this theory, it looks like it could lie in the middle here. At the same time, it's sort of as structured as equilibrium. It has area law, it has noise robustness, but at the same time, just by definition, these objects has to be feasible because they're intended to capture something that could, in principle, exist in nature. Okay, so maybe metastable state is something that we could try to aim for in thermal simulation, and if that is the case, there's sort of big room for sort of understanding this both experimentally and theoretically. Okay. So thank you, and I will stop here.
Okay, we have time for a couple of questions for Anthony.
Is there a sense of insensitivity to initial conditions when I'm looking at local observables? Like I'm getting at, so we know that after full thermalization, local observables would equilibrate to whatever expected value Gibbs we expect from the Gibbs state, but when it hasn't yet equilibrated and it's already in a metastable state, can we argue that different initial states, like if you run the same dynamics on different initial states and they are in like different metastable states, local observables are nevertheless similar?
Well, there's an example where it's not similar, which is the 2D Ising model. Because you could get stuck in kind of mostly up or mostly down. And if you're in mostly up, you get stuck there for a very long time before it really flips to the other side. So I guess classically, there's this symmetry broken thing seems to be if you start looking at something that, if your system just looks like it's mostly up, you would just stay mostly up. So that is sort of the counter. But counter example, I think in quantum system, maybe things are a bit different. So I don't know quite exactly what could happen. It could be that everything just ends up having the same value locally, but they're actually secretly different. I think that's the case for quantum memories. So I think there could be very different behaviors.
Thanks.
Thanks for your great talks. It's really interesting that you can construct the Liouvien to fall into a thermal equilibrium state, but it also got me intrigued because you need a certain structure in the Liouvien, and like it makes me wonder, like when nature naturally equilibrates itself, I wouldn't expect the nature to have those forms of Liouvien. So like how should I think of how nature actually equilibrates relating to your line of research?
Yeah, so that's an open problem. So in some sense, when we define these Markov chains, or even in classical world, we try to describe hard disk using Glauber dynamics, that is always a very simplified model, right? Whether nature is really doing that, I think that it might be sufficiently accurate in some case, and maybe not. And then in this extra case, maybe you do need to take into account sort of non-Markovian effects or non-detailed bands effect of noise. So I think maybe some cases it would be these kind of effective model would work, and in some other case one to start adding corrections to get those. But I think right now my view is that this is at least a first order approximation of description of nature, and in particular this is a framework that one can start proving things and have a concrete kind of falsifiable discussion about this particular model. Right? Whether it's really the true model of nature, I think in some problem regime, people actually are able to prove this can be derived in some natural setting. But then there are always lots of assumptions. So right now, I think toy model is like a tractable, and then a succinct toy model is at least a good start. Yeah.
Okay, I think let's thank Anthony and all those speakers this morning again. And we now have a lunch break, but I want to encourage everyone to be back here on time at